Hello, AP Calculus students. Today we're starting our first adventure into Chapter 4, 4.1.1, and you'll notice the question at the top here is, how can I calculate the exact area? We've dealt with in the past finding the approximate area under curves by using rectangles and trapezoids and things like that. We should take a minute just review the idea. Fredo and Frito was a problem we looked at way back in Chapter 1. And the big idea, let's just jump into question B right away. Don't worry about those two graphs right there. Question B is going to say, recall that the slope of a secant line can be used to determine the average velocity at any point on the curve. The question is, how can the exact slope of a curve of a point be found? And this is what we've been dealing with in chapters 2 and 3 right now. If you think about some sort of curve off to the side, we'll just kind of draw a quick curve like this. Instead of being concerned with the secant line that connects 2 points like this, what we do is we actually push those 2 points as close as possible together to the point where there's only 1 point, and then we look at the tangent line that's there. So this question is really just reviewing the idea that the slope of a tangent line is going to be the exact slope of a curve. How can the exact slope of a curve be found? You find the slope of the tangent line. Or we might say the line tangent to that point. Now, this is going to seem like a weird question out of left field because it has almost nothing to do with what we just talked about, but rectangles can be used to approximate the area under the curve in order to calculate distance, make a conjecture about how the exact area under the curve can be determined. And believe me, these two things, question B and question C, are related, but that's kind of what Chapter 4 is all about. Chapter 4 is called the Fundamental Theorem of Calculus, which can be summarized in basically one sentence. Derivatives, and what we don't know yet, but we're going to learn about today for the first time, integrals are opposites. It's an idea that's been kind of hanging out in the wings waiting for us to talk about it, and we're going to talk about it in this chapter. Derivatives and integrals are opposites of each other. That's kind of the thing there. So getting back into question C, which does seem like it's out of left field, if you look down at the graphs that we're going to look at in the next question in 4-2, you can see a good visual of exactly what we're talking about here. Is that obviously the more rectangles we choose, look at the difference between the 4 rectangle graph and the 200 rectangle graph. Which one's more accurate? I mean, 200, the more rectangles you choose, the more accurate your curve is. And trust me, those are actually rectangles, but they're so small that you never even know. The human eye can't even detect their rectanguliness. So, yeah, right? Making a conjecture about how the exact area, basically this, use infinite rectangles. Which you might think is going to make the sum absolutely monstrous, because it's going to mean more rectangles means more things you're adding together. But the thing you got to remember is that as you use more rectangles, the rectangles themselves get smaller. So you're adding together more and more and more small things, which is going to add up to the same basic sum. But the more rectangles you use, the more accurate it is. Let's look at question 4.2 to help us kind of solidify this visual idea. All we really wanted to do in 4.1 is get kind of a review so far where we are. Question B talks about derivatives, and question C is really talking about what we're building up towards today, which is the idea of an integral. Calculus has basically 2 parts to it, derivatives and integrals, and everything kind of revolves around these 2 ideas. 4.2 says that regardless of which value of n is chosen, a Riemann sum can only approximate the area under the curve because rectangles either add extra area or miss some area. And some values of n give better approximations than others, but even this 200 rectangle thing here is still going to be a guess. It's not going to be exactly correct. As far as your observations going on here, I mean, more rectangles is more accurate, is probably the correct answer for part A. More rectangles, more accurate. But question B is going to come along and ask the question, how can we calculate the exact area? Well, what we're going to do is we're going to use our old friend from way back to the beginning of this class, is the idea of a limit. We're going to take a Riemann sum with a number of rectangles, because think about this, the Riemann sum calculation has the variable n in it, I equals 0 to n minus 1, and you have this b minus a over n thing. What we're going to do is take our Riemann sum calculation. I'll finish writing the whole thing down. F of a plus b minus a over n times I. This is a thing that we've seen sporadically on homework assignments, and I know it looks really bulky, but we've been practicing it little by little as we go forward. So hopefully it's not completely foreign to you still. But the idea is that we're going to stick right in front of this thing. We're going to do the same thing we did with limits and derivatives. We're going to put limit as n approaches infinity in front of it. Essentially taking the number 200, or the number 16, or the number 8, or the number 4. What if it was infinite rectangles? What if we basically, instead of drawing rectangles, what if we're just drawing vertical lines that we just shade in the exact area? That's exactly what we're going to do. I think the best example for B using complete sentences would be to use a limit to make the number of rectangles approach infinity. And look at that, it's kind of written there for us too. Before you get panicky about this big blocky thing we have right here, don't worry. In a second, there's a math notes box that's going to introduce some new notation that makes this just so much easier. And we're never going to see sigma again after we start using that, except for on a few review problems every once in a while. It's kind of like derivatives. The formal definition is messy and ridiculous, but power rule and things like that makes it a lot cleaner later. It's very similar. Here's a good question to think about too. In question C, the width of each one of these rectangles is represented by b minus a over n. That's what we call delta x. So what happens to delta x as more rectangles are used? I mean, here's what happens, that b minus a, that stays the same, but n goes to infinity. And so what happens here is that this is basically 0 over time, because b minus a is a constant number that's not changing. If you divide that constant width of the area you're looking for by more and more and more and more rectangles, each rectangle basically becomes a width of 0. Basically. Doesn't actually ever get there, but that's what you got to think about. So a bigger concept here, if you just draw a quick little sketch of some curve like this, if we're trying to approximate the area between A and B are kind of fixed points. They're not going to change. And b minus a, also not going to change. But the number of divisions that we make in between a and b is what we're talking about going to infinity. And if you try thinking about these rectangles being very, very, very small, you're basically just drawing little vertical lines and filling in the exact area under the curve as you go. It's a very conceptual day today as we talk about integrals for the first time. Let's take this idea a little bit further and let's go to the next page and talk about 4.3, calculating exact area. Let's go ahead and write a Riemann sum. We'll review our process here for a minute and then think about the structure inside of this equation. So in case you haven't done it in a while, it's also on the math notes box right underneath here. For question A, the Riemann sum, to write an expression representing the exact area under some curve f, the nice general one, it's sigma from I equals 0 to n minus 1. We have b minus a over n, which represents the width of each rectangle. The same width that we said is essentially going to be heading to 0. And we're going to multiply that times the height of each rectangle. The height of each rectangle can be found by taking the function value of it. What's the y value as you plug in these x values that we're chopping up. Now each x value is going to start with a. A is kind of the left boundary of this thing. So we start with a, but we want to add on each width of the rectangle to get to the next rectangle each time. So we take that left endpoint of a and add on this b minus a over n thing. That's the width of each rectangle. And we do that I number of times, which comes back from the sigma. Essentially, if you break this down and really think about it, it's nothing more than the area, if I can spell the word length correctly. This is nothing more than, geez, I can't spell today. Length. This is just the area of a rectangle, width times length. That's the basic formula. But we're going to start thinking about this thing in some different ways. Question B asks us, will delta x ever be 0? And it can't be. rectangles can't actually be 0. So this is no. No, because then the rectangle wouldn't exist. However, since this is calculus, and probably the most calculus idea that we can talk about today is the idea that we can send something infinitely close to 0 without actually ever getting there, that's exactly what's happening in question C. What happens to the area of each individual rectangle as n approaches infinity? Well, the width approaches 0. Therefore, the area also approaches 0. However, the area never actually gets to be 0. The width gets to be 0, but the height of the rectangle is kind of set by the function itself. So the area is kind of this little area problem where it's 0 times the height. And so question D, this is probably the most advanced visual picture we're going to think about right now. But if the area is composed of rectangles with areas that are approaching 0, why does the overall area not approach 0? And the answer here is that because we still have the heights. In other words, the function values, the f of x's, and there's an infinite number of these rectangles that we're still adding up. There are still very, very many rectangles. Even though each rectangle's area is approaching 0, the number of rectangles is also getting much larger. So each individual rectangle gets smaller and smaller and smaller, but together they're still adding up to be that same area under the curve that we're trying to find. It's okay today if this doesn't sink in completely. But we've mentioned before that the word calculus literally means tiny rock. And that's kind of what we're getting at here, is that if I want to find the area under a curve, I'm adding up a bunch of tiny little slices of that area until I get the whole thing. That's what we're doing here. By the way, I got to say, Dr. Strange uses the word calculus in Spider-Man Far From Home, and it's used exactly correctly. And I was like, oh. Also, Peter Parker says, "What's better than magic? Math," and that was a good line too. Okay. Here we're going to be introduced to a notation you've probably seen a handful of times here and there, but we're actually going to define it right now. And there it is, definite integrals. Right here, this is kind of the key idea today. Integrals are the opposites of derivatives. We've danced around them a handful of times. Antiderivatives are integrals. Area under the curve is expressed using an integral. But today we're actually going to learn what this notation means. So, a Riemann sum is a convenient way to approximate the area under the curve. However, in order to get an exact area, an infinite number of rectangles is needed. Since we cannot algebraically evaluate the sum of infinitely many rectangles, we're going to use a limit. In other words, the limit as the number of rectangles approaches infinity. There it is, hanging out right in front of this summation notation right there. And a much better way to write all that sigma nonsense is this expression right here, which you're going to be familiar with very quickly, a lot of it right there. That is the exact area under some curve f of x from a left endpoint A to a right endpoint B. That's it. You don't need that sigma nonsense. You don't need all the other stuff. That's the exact area under the curve. I think it's worth mentioning that A and B are the same as they always were. A is the left endpoint, or the left goalpost, I like to say. B is the right goalpost. And you no longer need to worry about n, because n is now going to infinity. So the other nice thing is you almost never calculate these by hand. In fact, we won't ever do it. There are formulas and easy ways. There are a lot of different ways to get it. Cool math fact, by the way, cool math history fact, it should not really be a surprise that the Greek letter sigma, which is basically the letter S, which stands for the word sum, is there. And also this integral symbol is also a big stretchy S, which also stands for the word sum. It's the same idea. You're adding up a bunch of things. This symbol, integral symbol, represents the S of sum, which is the German word for sum. A couple other notes things. All rectangles are of equal width. And for an example here, you'll see how easy this gets. If I want to find the exact area under the curve of this function f of x is x squared plus 1 over the interval from -2 to 3, you could write all of this nonsense over here on the left. That's ridiculous, though. You could write all that, or, and the sooner you can get used to this notation and start reading it as you write it, it's even better. This is the area under the curve from -2 to 3 of x squared plus 1. Good question. I'm glad. I hope we talked about that. Now, dx is, for the most part, it's a placeholder that you could probably not ever really understand and get through calculus very fine, myself included. I'm on the evidence. It's me. However, what I really want you to see is that this is still a rectangle. X squared plus 1 is still the height of that rectangle because it's the function value. Dx stands in for the width of that rectangle. In calculus, dx, the letter D, essentially stands for a small amount. So if you really think about what's going on here, I'll actually just draw the curve x squared plus 1. It looks something like this. Actually, let's go from -2 to 1. How about that? -2 to 3, sorry. I mean, that integral is asking you for this area. From -2 to 3, the area under the curve, like there. Now, what we're doing here in this integral is we're chopping up that area into many, many, many small rectangles. If you were to zoom way in on one of these rectangles, it would look like this. Its height would be given by x squared plus 1. And its width is dx. A very, very, very small amount of x is what that means.
So we don't really need it, but like
you do need it because it's correct. It's got to have a dx there. And it can mean a lot of different things. But you'll notice that x squared plus 1 does have to go in parentheses because it is a thing being multiplied by the width. So you do need it. A lot of times it's just used to designate which variable is the variable, in this case x. But if you can see it as a length times width thing, that's a good idea too.
Do you ever have to plug anything in for it?
No. Yeah, that doesn't really... There are going to be some problems later on where we'll use it as kind of a pseudo variable, but for the most part it just kind of stays there as a signal that we're talking about with respect to x. It is a thing we'll do later on in this class where we'll use integrals going horizontally instead of vertically. And in that case, we would say dy instead of dx, but we'll talk about that later. Okay, let's actually put this to good use. For the most part today, we're not going to deal with formulas. We're just going to be doing geometry problems, really. So let's take a look at 4.4. And then hopefully we'll get these done and we can get back and work on that test. So just breaking down some things here. Notice the general form of the integral from a to b of f of x dx. The upper b and the lower a bounds represent the left and right endpoints. The left and right endpoints is what a and b are. The left is a and the right is b. I like to say goalposts because a lot of these times in these problems you're talking about the area under some curve, and it helps to think about like a vertical katana coming through and say, okay, from here to here. This is question B is asking exactly what we just talked about. If you think about what 1 over n is doing when you send the limit as n to infinity, basically what's happening is that is going to 0. But 1 over n used to stand for the width of the rectangle. And now we've kind of replaced it with this idea of dx. Regardless, they both stand for the width of the rectangle. And that width is being sent to 0 by the limit in front. It's not actually 0, but we're pushing it closer and closer and closer. Whenever you see dx, that just means a tiny bit of x. That's why derivatives are often written as dy over dx. That's a ratio to a little change in y to a little change in x. That's what slope is. Slope is y over x. Same thing. Explain why it's important to remember that we're multiplying because we're finding the area of a rectangle. This is exactly what we just talked about. It's important to remember that we are multiplying a length times a width to find this rectangle. In this case, x squared plus 1 is the height of that rectangle, and dx is the width of that rectangle. So you have to remember to put x squared plus 1 in a parentheses because it is a separate thing being multiplied by the width of that rectangle. But again, I'll point you to this drawing right here where to find the area under that curve, we're basically just looking at the area of several very, very, very small rectangles, each one of which has a height of x squared plus 1 and a width of dx. Same idea. So now let's actually get down to brass tacks and talk about how to actually calculate these. You were not allowed to use a calculator, and it's good because you don't need one. Let's just take a look at some examples. Question A, for example, is sine of 2t. It's the area under the curve from 0 to 2 pi of sine of 2t. So let's think about that for a minute. Here's 2 pi right there. There's 0. There's your A and your B. Sine of 2t is just a sine wave that has a period of, it's going to happen twice on this 2 pi. So this sine wave goes up and down and back, and then up and down and back. And our job is to find the total area under the curve from 0 to 2 pi. Got any guesses? 0. Very easy to do. The nice thing about sine is that it's symmetric to the x-axis, or not symmetric, there's a word I'm looking for. These little bumps are all congruent, is what I'm thinking of. So I actually don't, there's a way you can figure out, later on in this class we'll have methods for figuring out what the exact area is, but it doesn't really matter because whatever this chunk is right here, this A, it's the same as B. A equals, you might say negative B. Or, I don't know. They're the same area, but they're negative and positive. So they end up canceling out and becoming 0. You can do all these problems if you haven't picked up yet. You can do all the problems here by simple geometry. You don't need any antiderivatives. You don't need any other methods. You can just solve them by looking at the graph. Let's look at B. B is a linear equation. Again, we're looking from negative 2 to 3. It's 1/2 x plus 3. So I always start with the y-intercept. 1, 2, 3, right there. The slope is 1/2, so if I go back in time 2 steps, I'll go down 1, right there. And then 3, let's see, over 2, up 1, and then it's going to be about halfway through right there. So it looks kind of like this. We're looking for the area of this shape. There's a lot of ways you can get it, but it's a giant trapezoid. I think that's probably the best way to do this, is to think about it as a trapezoid. And its area is 1/2 times the sum of the bases. This one is 2. This side over here is going to be, you gotta think about it for a minute. 3 times 1/2 is 1.5, and 1.5 plus 3 is 4.5. And that's all over the width, which is 5. All the way down there. So these questions are less about calculus and more about reading the notation. 2 plus 4.5 is 6.5. 6.5 times 5 is that number. Ends up being 32.5 divided by 2, which is 16.25. Question C is another fun one. The area under the curve from 0 to 6 of 4. Is there any guesses right now without drawing it?
24.
Well, you're on fire. 24. Exactly correct. Oh, it's okay. We can draw. This is an easy one to draw a quick picture of. It's just going to be a rectangle. The width of that rectangle is 6, and the height is 4.
Oh, yeah.
This is the same question. If you want to go back to chapter 1, we've been setting up for this for a while. This is the same as saying, hey, a car is going 4 miles per hour for 6 hours. How far did it go? 24 miles. Yeah, because the speed is represented here. This is 24. That's it. The same kind of thing happens, D is another easy one too if you graph it. I was thinking there might be a trick with the mismatch of variables, but not the same thing here. D is another one that's probably worth a detailed drawing. We got 3 times k squared. You'll notice the variable has changed. That doesn't do a whole lot. It just means that k is the variable. But we're going to treat it like x anyway, because that's the only way we really know how to draw it. So 3 times k squared is going to be a parabola. I don't know exactly what it's going to look like. It doesn't actually matter. You'll see pretty quick what I'm talking about. The thing about parabolas is that they are even functions. So if we say that's -4 and this is +4, the thing about parabolas is that they're going to be... sorry. Guys, I'm sorry. I thought I saw a little negative sign in front of there. Whoops. This is way easy. This problem's easy too. Any guesses? 0. Sorry. I was doing an entirely different problem in my head. I apologize for that. This one doesn't... This is a really common, just a property of integrals, but the integral from a to a of anything is just 0. Because now there's absolutely no width going on. A to a is just the same point, so there's nothing there. That's it. The question I had in mind was a question that's on the homework later on. I don't know if I did my notes on this page. No, I didn't. On this one, this is 4-7. This is on the homework. But in this question, they tell you it's an even function. And they tell you that the integral from 0 to 2 is 10. So that area is 10. And they ask you what the area from -2 to 2 is. And what you got to recognize is that that's also 10. So it's 20. Because you have the same area on the left and the right. You add them together. A lot of integral problems end up being easy to do if you break them down into easy geometry situations, if you can. Okay, that's very cool. That was nice, and thank you guys for watching this. You guys are awesome.